Thanks. I'll begin. Heavenly Father, we thank you for this morning. Thank you for these students. I just ask that you bless our work today. And again, Lord, we just pray that you be glorified in what we do. In my prayer, Lord Jesus. Amen. So, let's see, just a comment. I probably shouldn't even write anything, but we were thinking about working over like q adjoin pi or q adjoin pi cubed. And it is, in fact, the rational functions. I mean, it is, q adjoin pi is the same as q adjoin x. And the smallest field, which has x and q in it, is the rational functions over q. And then the thing is, we were looking at questions of linear independence and doing some things. Now, we're behaving like those were polynomial equations, and then we kind of were like, why, it's not actually a polynomial equation what we're doing. But can you guys think of the simple thing we could do to make it into a polynomial equation? What's that? Or either pi of x or the pi of x cubed. Either one of those, if you're looking, I mean, those are it's either rational functions in x cubed. It's either rational functions in pi cubed over q, or rational functions in pi over q, essentially. I mean, there's a natural identification there. So what you can do is just clear out the denominators. You multiply by the necessary product of the denominators, and that converts it into a corresponding polynomial equation, and then you can just directly use the linear independence you know and love from there. I think that was missing from our discussion. Yeah.
I think I noticed that yesterday.
And I think that was also the thing that was kind of gnawing at us. Like, we were like, but we didn't quite formulate it yesterday in words. But I think that was the other kind of missing piece. Bill pointed out so I was talking to Bill about it, just trying to make sure I'm not missing some giant, thing. But I told you guys if you look at the Wikipedia page, it mentions that q adjoin pi and e is not known to be the transcendence degree is it 2 is not known. Yet, consider this disturbing fact. In one of your homework problems, I think it's one of the ones I signed you, you look at alpha and, is it alpha beta or did you look at alpha pi and e? Alpha beta. You can do that same problem with pi and e. And in so doing, you can prove that at least one of alpha plus beta or alpha times beta has to be transcendental. It could be that both are, right? But that simple relative, that's a pretty simple problem, proves that at least one of them is, and yet it's at the moment unprovable, or no one's proved whether or not both of them are, algebraically independent. So it seems like that homework problem is significant, like progress towards that end, but it just, no. I mean, anyway, it's open. I don't know, this is the thing, is I'm not sure if it's one of those open things or if it's one of those things that's been shown to be unprovable. Yeah, that I don't know. But
from the wording, it sounded like it was just open.
Yeah, that was my impression of the Wikipedia page. But okay, so what's a splitting field? Provided there exists what, like alpha 1, alpha 2, and alpha n in K, and, of course the, if you allow me this small manga style comment, an, x to the n. Right? So there exists these alphas such that what? The leading coefficient is still a sub n. That's from the field, not necessarily the extension, although it could be. I mean, well, if it's in the field, it's in the extension, right, by construction. And what do we know about splitting fields? What do we learn about splitting fields in this section? Well, I guess first we learn how to find them, right? And I wouldn't say we've really learned any especially new calculational technique here either, have we? I mean, if you really, I think it's fair to say that we've been doing the algebra we've been doing, since I'm not sure when for you exactly, but I don't think we've really learned any new secret algebra tricks so much. Well, that's not entirely true, right? I mean, I think that the new thing comes from the extension degree theorems, right? The divides by arguments, the kind of sneaky, circuitous proofs of irreducibility. That's where there's really something new. So yeah, that's the idea. Now, the ultimate point in this section, let me just read these theorems rather than writing some of them down. If we have an isomorphism of fields, right? Actually, I can write this diagram. So this is theorem 27 in a picture. So what we got? We have isomorphism sigma that goes from E to E prime. We have another isomorphism. I can't talk today. Isomorphism. Good. I've lost the ability to say isomorphism. That's not a good sign. Let's see here. F prime, like so, right? Both isomorphisms. And let's see what's given here in the theorem is the isomorphism of the base fields. All right. And E and E prime are splitting fields. All right. So these are, and this isomorphism, you know, they're splitting fields also with respect to the natural isomorphism between the bases. And that natural isomorphism we talked about in a previous lecture, right? We take f of x, remember, and we map it to what? We called it like f prime of x or something like that, although that's not the derivative. And so, I mean, this is this kind of map, right? It's not even one of these. But you know, just to since it's been a couple classes since we did it, it would be something like if we take a0 plus a1x plus da 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 plus an x to the n. Well, under this isomorphism, under the induced isomorphism from phi, right? This is the extension of phi to polynomials over f and polynomials over f prime. We just map the coefficients, right? So that was the that's the induced isomorphism on the polynomial ring. And then, so this E splits this splitting field for f of x. This one splitting field for f prime of x, the natural corresponding polynomial with respect to the given isomorphism phi. This one's given. And what the theorem basically does is it says, hey, there exists this sigma that is an isomorphism between the respective splitting fields of f of x and f prime of x. And not just that, that isomorphism of the splitting fields naturally also restricts to phi. So if I take sigma restricted to f, I just get phi. And that's basically what theorem 27 says. And the proof is by induction, and it's pretty. And then the corollary is perhaps as important as this theorem that was the corollary, say, corollary 28. Corollary 28 tells us that any two splitting fields for a polynomial f of x over f of x, sorry, are isomorphic. Any two splitting fields for f of x in f of x, f a field, just in case you thought f was something else, you know, are isomorphic. So you guys tell me, how does that corollary immediately follow from theorem 27? Let f equal f prime. Okay. Ah. And what's the phi? Very good. So you take the identity isomorphism going from f to f. These are two possibly different splitting fields. Well, this proves that they're isomorphic. Yeah, the other thing is that there's a, I've neglected the, did you? That means isomorphic. And the lower did it is given in the statement of theorem 27. The upper did it is what theorem 27 says. I guess they're actually called tildes. Here, I'll tell you, we circle in green what the theorem actually gives us. The theorem actually gives us this and this. And that sigma restricted to f is equal to phi. I mean, those are the punchline of theorem 27. If we have an isomorphism between field f and f prime, if we have splitting fields e and e prime over those, with respect to the natural polynomials to split, then there exists an isomorphism of the splitting fields, and that isomorphism restricts to the given isomorphism. And as Sam has told us, if we take the case that the fields are equal and the phi is identity map, then we get that any two splitting fields for a given polynomial are isomorphic. Yeah.
Under corollary 28,
Uh-oh.
it has some weird notation with f of x and then equals f prime of x.
Oh, okay, so what that means is the f of x refers to e,
Okay.
and then that it's a parentheses, it equals f prime of x for e prime.
Okay.
It's kind of an odd use of like saying symmetric and anti, like sometimes you'll see sentences like anti-parentheses symmetric, then the matrix is equal to, it's equal to like parentheses minus its transpose or something like that. It's that kind of syntactical construction. It's, yeah, nothing especially interesting.
I think it's just saying f of x is equal to f prime of x, but that's not the main point of the sentence.
Very good. It's the sort of insight a computer science major has. It's good. Part of the shirt. Anyway, the field f bar is called the algebraic closure of f if f bar is algebraic over f, and if every polynomial f of x and f of x splits completely over f bar. So f bar is said to contain all the algebraic elements. So, definition, f bar is algebraic closure of f if each f of x in f of x splits in f bar, and over, I should say. And now, I'm not saying that f bar is the splitting field. It's probably too big to be that, right? But I'm saying, what I'm saying is f of x factors into linear factors in f bar, which is not to say that the splitting field is smaller, right? For example, real numbers, right, have this equal to what? Well, there you have other problems. It's not a field, but
But if we have Q and then we have Q bar is
what you want to ask is,
small algebraic.
is like the set of rational functions over the complexes
Right.
an algebraic closure of the reals.
But like for instance, if we have Q and then Q
Uh,
bar is given in the book, then
well-
C would also be an algebraic closure of Q.
Let's see here. I'm trying to see if he's got a minimality in.
If you go to corollary 32, it says that the complexes contain an algebraic closure for any of its subfields.
But they also are an algebraic closure for any of its subfields by the definition.
Okay, so yeah, I would agree.
Yeah, I think you're right. At least as the wording, as I parse it right here, there's not an expectation of minimality, so you could always adjoin other elements. But I also think in terms of common usage,
Right. That's why
people are usually wanting the
it seems like
smallest. Yeah.
seems like a poor definition in the book. I can't tell.
I don't know. I mean, I can see your. I don't know if there's something else out there that makes. I mean, that makes tacking on that it's the smallest. See, but that doesn't really make sense either. Well, this is. I mean, there's isomorphic. As you said, it's not. It's an algebraic closure. It's up to isomorphism.
Well,
I mean,
no,
that's
because
but that's
all
not it.
algebraic closures would even be isomorphic. So you can have some that are just big.
Yes. I'm just saying that even the notion of smallness would have to also, pay attention to the fact that the.
Because when we define a join, we already are given a superfield, and then we just say the smallest subfield of that remaining is.
That is true. Yeah, that's right. F adjoin alpha, beta, even an infinite list of alpha, beta, alpha 1, beta 1, blah, 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 whatever. That's all happening inside the universe of K, which is given from the outset. Here, the algebraic closure is we're inventing this new universe in some sense, right? I mean, it's, but well, anyway, an algebraic, we can fix it with the word an,
Or
right?
we could say if there's no subfield that also satisfies this.
Or there's no subfield that satisfies that condition. Yeah, that seems fair. I'll have to. Well, you can look into it too if you come to a definitive answer one way or the other. Let me know. So we at least this is an algebraic closure. But my larger point was that this is not the splitting field. For example, x squared plus 1 has what splitting field? Oh, Q, listen to me. I'm thinking of it as a real polynomial, right? So let's not be dumb. I mean, this is, I'm saying in there, right? The splitting field in there is what? Just, yeah. No, I think it, oh, dang it. You're right. It's R adjoin I, which one of your homework problems essentially proves is C. Curses. Let's try this again. Well, that didn't go as I'd hoped. How about Q? The rational numbers has Q bar algebraic closure, right? Where Q bar is the set of all algebraic numbers, which again is countable as we talked about. And in there, you have x squared plus 1 is in Q of x, right? But certainly Q bar is not the splitting field for x squared plus 1. Q adjoin I, right? A smaller splitting field, of course, because
we can't make square root 2, for instance.
right. There's no root 2, there's no root 3. There's many, many things in Q bar which are not in Q adjoin I. Infinitely many, in fact. So.
Q bar infinite dimensional over Q. I guess it must be right.
Is Q bar infinite dimensional over Q? Yes. Because, for example, x to the n minus 2 is irreducible for any n. So, and you can prove that, well, I think those are independent in some sense.
Somewhere for n prime.
Yeah. Oh, prime. I should probably need prime, yeah.
But I can't remember where it is.
Now, we also have proposition 29, which tells us that if we have an algebraic closure, then it's algebraically closed. So it seems like it's good terminology. What does algebraically closed mean, though?
I have a slightly different definition. Algebraically closed means that every polynomial has a root, which translates to, like, is equivalent to say that it's closed.
Right.
But it's interesting that they do different.
Yeah, it's right. So I guess algebraically closed is a statement about zeros, whereas algebraic closure is a statement about linear factorization in our current terminology, right? And then finally, so then he gives this beautiful proposition 30, which says that for any field there exists an algebraically closed field, K containing F, that argument by Artin, which is rather subtle and uses Zorn's lemma. And then proposition 31 says if K is an algebraically closed field and F is a subfield of K, then the collection of elements F bar of K that are algebraic over F is an algebraic closure of F. And an algebraic closure of F is unique up to isomorphism. So I guess he's now doing things inside a universe. See, so the difference between proposition 31 and the discussion we were just having is he starts with an algebraically closed field. He looks at a subfield of that. Then he talks about the algebraic closure of that subfield.
But K itself, under the definition, should be an algebraic closure of F, right? I don't see any way in which it's not.
Yeah.
So that seems like his proposition is false, as stated. Because otherwise there would just be that you're always kind of the subfield of K.
Hmm.
Yeah, and then you would always have F bars equal to K if what he's saying is true. So it seems like just a mistaken definition.
Well, if you look at here, he's now referring to it as the algebraic closure as opposed to an algebraic closure.
Right, and that would be like that would be true if it were.
I think he's assuming. I think he's assuming that it's that.
Yeah.
Well, I don't know. Again, I think the difference between previous discussion and this one is that he's starting out with a, he's already put the subfield inside an algebraically closed field,
Yeah, I agree.
and then
But the difference is, like, the concern you were raising before was about up to isomorphism versus, the concern here is that they're not even the same up to isomorphism because they're different sizes. Because, like, the only way that what he's saying can be true, given this definition, is if F bar is always equal to K.
so I think, is everything fixed here for you if we say that F bar is the smallest extension
Yes.
that in which all elements in F split?
Yeah.
Okay. All right. Well, I will, again, try to look into that. But I think it's probably the case that it's just omitted from the definition and understood. Yeah. I think that's the easiest way to connect the dots here. And then, of course, the theorem, fundamental theorem of algebra, the theorem we know and love. The field of the complex numbers is algebraically closed. And then corollary 32, the field Field C contains an algebraic closure for any of its subfields. So there's Q bar, and what are the other subfields of complex numbers? In any event, yes, if you take in complex analysis, you might have proved that in there, right? There's this analytical proof, which is rather beautiful, from complex analysis, proof by contradiction and Leibniz's theorem. There's actually about a dozen proofs in complex for the fundamental theorem of algebra. And it's one of the joys of teaching complex is finding all these different proofs. But for us in here, I actually have it as a homework problem for you guys in the next part of the course. Because once we develop the machine of Galois theory, we can prove the fundamental theorem of algebra using it, which I think is kind of neat. And it wasn't that hard either from what I looked at. But we'll get there. All right, so that brings us to section 13.5, which is on separable. Separable and inseparable extensions. So let me just basically define the terms here. Definition, F is separable. Oh, is it? Excuse me. Yes. So not F, but f of x in fx. F joint x is separable if it has no what? Okay, no multiple roots. Roots where? So, I mean, example. If we had x squared plus 1 squared, right, in R of x, that's got no real root, right? So that must be separable, right? No, wrong. It's in the splitting field. Yes, we have to care about the splitting field. When we're talking about roots where you can find them, in the splitting field. Right? So in fact, this is an inseparable polynomial because, as you guys know, x squared plus 1 squared is actually equal to x minus I squared times x plus I squared. It has double root, right? It has an irreducible factor squared, 2 of them in fact. So this is an inseparable. Inseparable polynomial over R. Another example, of course. I mean, he always comes back to this, doesn't he? X squared minus 2 is what? X minus root 2 times x plus root 2. So this is separable over Q, right? Of course, the splitting field is what? Q adjoin root 2, right? Now this one, this was his example 1 actually, if you're counting. His example 2, a little bit more unsettling. So if you look at x squared minus t, oh look, here's another use of the parentheses here that's bothering you, right? X squared minus t in the finite field with 2 elements adjoined t. So really, this is rational functions up to isomorphism. This is rational functions of z2 polynomials in the variable t. If we want to look at it that way. Anyway, this is it's an infinite field, right? But it has characteristic 2, which means, of course, that explains the parenthetical comment x equals x squared plus t, because he's added 2 copies of t, which is like adding 0, right? But in this we have, let's see here. How's it go? Sorry. So, goodness gracious. So there exists the square root of t, right, in some, extension of this. Right? And in that splitting field, what do we have? We have x squared minus t is equal to x minus the square root of t times x plus the square root of t. But what does that give us? Then, remember, we're in a field of characteristic 2, right? So if we add 2 copies, pick whichever one you like. If you want to subtract 2 from this one or add, however you want to go. What do you guys want me to do? Add 2 or subtract 2? Emily, your choice. Add 2, all right. This is x plus root t. X plus root t. And all of a sudden, we've got x plus root t squared. So this shows that this is what? Inseparable. All right. So his next move is to define a formal derivative. So, if you ever teach, I think if you ever find yourself teaching Math 200 at some point in your life, and you guys might, somewhere, in some context, that kind of course, Introduction to Proofs, or even just like an honors calculus, I think one of the great exercises you can give is just to prove the product rule for polynomials, but you could just give it as an inductive thing. You could do induction on the degree of the polynomials or something like that. I'm pretty sure you could prove it. But it is, in fact, this can be done, of course, completely without limits, but the derivative with respect to x of f of x is what? I'm sorry, I'm not trying to invent my own notation. No, notation. What? There's a new word for notation, which is in itself, some sense, kind of the problem I was just talking about. Let's see here. No, dx, f of x, yes. So we could think about this dx as like an operator, of course, an, x to the n, a2, sadness, a sub 2, x squared, a1x, plus a naught. And you know the drill. This is equal to what? This is the definition for us here. N, a sub n, x to the n minus 1, 2a2x1, x rather, plus a1. And it's a simple algebra exercise. Like I said, this would be great for an introductory proofs class, just to give these as kind of nice, perhaps, I think they could be interesting induction proofs or something like that. Right, so we got, and then of course also, what else do you know about this derivative operator? It's a derivation. It's actually an endomorphism of the ring of polynomials in the sense that it satisfies this Leibniz rule. And also, of course, if you have f of x plus g of x, what do you got? To get that it's an endomorphism, I need one other thing, I suppose, right? mean, saying a linear transformation with the Leibniz property is a derivation. Why do we call it a derivation? Because it's like, yeah, so this is kind of the somewhat circular comment saying it's a derivation. But it is. And then the neat thing is, of course, that looking at the derivative and comparing it to the function reveals the presence or absence of multiple roots. Maybe you never thought about this before. I don't think it gets emphasized much in my abstract algebra, if at all. But let's just look at an example. Suppose we had f of x equal to, x squared times x minus 3, right? Then if you calculate dx f of x, that's what? X cubed minus 3x squared, which gives me what? 3x squared minus 6x. So we can factor this. What do we get? Three x times x minus what? 2, right? So you notice that I can say a little bit more. You can even see, if you do this, you can even see which roots are repeated, right? I mean, the fact that there's a common x in both of them shows you that 0 is a repeated root. The fact that there's not a common x minus 3 factor in both of them shows you that x minus 3 is not a repeated root, in fact. But the larger observation is that if the greatest common divisor of f of x and the derivative, right, if that's equal to 1, in other words, if these guys are relatively prime in the polynomials, right, then f of x has what? No repeated root. Or should be more careful here. Proposition 33 says what? It says a polynomial f of x has a multiple root alpha if and only if alpha is also a root of the derivative. That is, if f of x and the derivative are both divisible by the minimum polynomial for alpha. In particular, f of x is separable if and only if it is relatively prime to its derivative. Oh, we have notation. This is the wrong notation. We don't do this. Sorry, I gotta get with the program. Dummett and Foote's notation for relatively prime would be this, comma that, equal to 1. Right. Which is to say that the ideals, in fact, the principal ideals, which are generated by f of x and its derivative, respectively, are co-maximal. Yeah. Which is the bigger version of relatively. I mean, for us, we say that integers are relatively prime when their greatest common divisor is 1. But if you look at the integers, right, the ideal which the one generates, the ideal which the other generates, and you add those together, you take the sum of those ideals. If that contains 1 in it, right, then it's going to generate the whole integers.
So here by 1, do we need the ideal generated by 1, or do
Yeah.
in other words, the whole ring?
No, that 1 is 1. I mean, we're talking about a ring with unity.
Right.
I mean, we can capture whether or not the sum of the ideal generated by f of x and the derivative is the whole ring. It's sufficient to. I mean, that only happens if 1 is in there.
Right.
In that ideal.
I'm just trying to think, because I know that he uses parentheses to define the ideal generated by a single element. So if you say.
Oh yeah, I mean.
Is
I think to be pedantic, you're probably right. This should be that.
But
I may be maybe I should say the ideal generated by both of them. It's not just adding. It's what it's.
Well, no, because it would be.
How do we generate a new ideal from two given ones? I think we take finite sums of products. Well, how would you do it for 2? And if you have, the ideal generated by 2 and the ideal generated by 3, and how do you use those to get all the integers? I mean, it's not just it's not just a. I think it's just a sum of things in each. Actually, I think it is just a sum of things in each. I don't know, anyway, I'm getting way off track at the moment. But what I wanted to point out to you is that this idea of relative primeness is explained in Dummett and Foote in terms of ideals, and I think comaximality as opposed to, what was more common for us last semester, the greatest common divisor idea. Although last semester so long ago, I've forgotten where we got to in terms of sophistication. I can't say words. So let's look at an example. So let's see here. Again, this is if and only if f of x is what? Separable. I mean, proposition 33 has more than just this in it. It actually says, alpha is a multiple root for f of x only if the minimal polynomial for alpha divides both the polynomial and its derivative, just like we saw in my example, right? The minimal polynomial for 0 is what? It's just x, right? So x divides this, and x divides that. The minimal polynomial for 3 is x minus 3. It divides this one, but it doesn't divide that one. So there's proposition 33 in action. The examples here are quite interesting. So, but I don't have time to do the examples. Just let me save those for next time. Sorry, I'm, as usual, behind. But not really, because I got tricked into jumping ahead by Jonathan, so I appreciate that. I wasn't really a trick. I mean, you guys are just trying to get somewhere in your homework, I understand. But the other problems in your homework, which probably were up till now mysterious, may start to be unmysterious, right? Like, how do you show something is, you have those problems like show something about this polynomial in any extension field of Z3. That seems very daunting until you think about, think about the splitting field. And you think about this theorem in terms of whether or not roots are repeated. You can look at the derivative, right? And this is also very interesting. So, you look at this, and you notice that this is definitely a polynomial of degree n minus 1 if we're working over characteristic 0, right? But if we're in characteristic P, then all of a sudden we can drop degree in the derivative. And so like the last half of this section is basically about coming to terms with how that all plays out for a field with finite characteristic. The devil's in that detail, the fact that we drop degree, possibly. But I'll tell you where we're going. Corollary 34 says every irreducible polynomial over a field of characteristic 0 is separable. So irreducible if and only if separable over a characteristic 0 field. And moreover, we can characterize a polynomial over such a field as separable if and only if it's the product of distinct irreducible polynomials. So, in other words, separable is interchangeable with irreducible, so we're not really aware of this concept in our ordinary experience with fields. That's why I think this is a slightly higher order topic, because really to understand, to appreciate this topic, you have to go past what you've already experienced in math, right? The new place where separable and irreducible have different meanings. It's a little bit foreign to our experience so far. The next 2 pages, he develops what's called a perfect field. A field of characteristic P is called perfect if every element of K is a pth power in K. And any field of characteristic 0 is also called perfect. This sets up the punchline of the section, which is, come on, here it is, corollary 39 at the very end. Every finite extension of a perfect field is separable. In particular, every finite extension of Q is either Q or a finite field is separable. So, in other words, to appreciate the distinction between irreducible and separable, you need to look outside the rationals and outside extension fields of finite fields. Like maybe, well, is it a finite extension? I maybe missed a word there. Finite extension. A finite extension of a finite field. This.
Wait, but that would still be a finite field, right?
Yes. Right. But is this, well, look at this example right here. Is this a finite extension? No, this is not a finite extension. And is this polynomial is irreducible? Is x squared minus t irreducible in here?
The book showed that it was, but I can't remember.
Yeah, it was technical, and I don't think I covered it, but you're right. The book has the details. Maybe we could we do Eisenstein? Is t a prime in this context? It seems like if t is prime, then we could apply Eisenstein to this. That might be a good exercise for us next time, is to actually get into the details of why this is irreducible. We haven't done enough of that yet in here. Let me take some time next class to prove that this is irreducible, okay? And maybe to prove Eisenstein, because I think that's missing from in here, and I really should have done it days ago. But I don't have no regrets. I think it's good that we forged ahead. Now we can go back and fill in a few more picky details next time. But you can see, anyway, this is irreducible. And it is also inseparable. So you need something like this to experience the weirdness. Anyway, I shut up. Thanks, guys.